Bismillahirrahmanirrahim. Before we begin chapter 8, which is about conic sections, we have to review a little bit about functions in general, and this also gives us an opportunity to review all the previous functions that we have covered. What I've drawn here, of course, is a very familiar picture to demonstrate the concept of function, and it's a very, very important concept, of course, and it's worth reviewing as much as we can. So what I have here is a set of numbers, so 1, 2, 3, 4, 5, and this set of numbers is related to this set of numbers, okay? And here it is, okay? And if the two set of numbers are just sitting there and doing nothing, as you know, then they're just two set of numbers that are sitting there and doing nothing. But if I relate one to the other like this, I say that 1 is related to the 3, and the 2 is related to 5, and the 3 is related to 7, and 4 is related to 9, and 5 is related to 11, like this. Now, these two set of numbers are now related. And this is said to be a situation of where you have relationship between the two set of numbers, or a relation. So when two sets of numbers are related, that is called a relation. All right. So a relation, such relationship is of two sorts. It can either be a function, and it can be a non-function or not a function. All right. So that's pretty easy to remember. And then the idea is when is this relationship a function, and when is this relationship not a function. So I have two sets of numbers here again. And if they are not related, just sitting there and they're not related to each other, they're just two sets of numbers. But when one number in one of the set is related to another number in the other set, then we have a relationship between these two sets of numbers, and that's called a relation. Now, and then I said, and relations are of two types. It is that relation can be a function, or it can be a non-function, or not a function. If you remember, of course, that all the numbers that are here, that's called the domain of this particular set of numbers, and everything over here is called the range. The domain and range are the elements of each set. So the elements of the first set, 1, 2, 3, 4, 5, constitute the domain of that particular set. And the elements of the second set, 3, 5, 7, 9, 11, represent the range of this particular relationship. Okay, and you of course know there are synonyms for this. A domain can be the input values, and range can also be the output values. OUTP, and then we can use any particular variable to represent the elements of the input. Typically we use x and y in algebra. You can use any variables, of course, and the range would be y. So domain, range, input, output, x and y, these are all different ways of referring to the elements of each set. Now, this particular set that I have drawn over here, there is some pattern of association. There doesn't have to be. I could have drawn some random sets like this, 1, 2, and 5, and this would be like pi and square root of 2. And there's no obvious reason why 1 goes over here, 2 goes over here, and 5 goes over here like this. So, but if there is a discernible rule that connects every input to output, and so that's called a rule. So what takes an input to an output, then that's called the rule. Okay? So if there is a rule, and nobody says there has to be, then that rule takes the input and converts it to the output. And you can say in this case, for example, the rule is this: y is equal to 2x plus 1. Okay, so in this case, the rule for this function is y is equal to 2x plus 1. So I take x, that's 3 times 2 is 6 plus 1. So that is the rule that converts every input to an output. Let me reiterate this only because this is so important. A rule takes the input and manipulates it somehow and converts it into the output. Another way of saying this is f of x is equal to 2x plus 1. So the rule is that you take the input multiplied by 2 and add 1 to it to get the output, or the functional output, okay, f of x. Okay. Now, another idea I wanted to convey over here, let me keep that there. Another idea I wanted to convey over here. This particular example has 1, 2, 3, 4, 5. Well, it only has 5 elements in the domain. In other words, this is a finite set of numbers. So you can say that the domain here is a set of numbers that's 1, 2, 3, 4, and 5. That's it. There's only 5 elements in the domain. And the range, similarly, is also finite. And the range constitutes these 5 elements: 1, 3, 7, 9, and 11. So, of course, you can have a relationship, a relation where the domain is infinite, and therefore the range could also be potentially infinite. So domain and range have to be defined, or have to be known or determined for every particular situation. But what determines a relationship to be a function and a relation to be not a function? Well, a function is a special subcategory relationship where every input, okay, will only give one output value. So this is the key difference between a function and a non-function, and that you must remember. For a function, one input has to give only one output. So you have one input here, it must only give one output. In other words, only one error can be coming out from a particular input from here. If there's one input like here and it's giving 2 or 3 or multiple different outputs like this, then it is not a function. In other words, for functions, let me try to draw it neatly over here maybe, you cannot have this. So that would be like for a function. So function, you cannot do that. So every input can give only one output. Now that doesn't mean that different inputs can give the same output, and that's okay. Different inputs can give the same output. That's still a function. But for a relation to be a function, every input must give only one output value. Every input must only give one out. So this particular relation that I've drawn for you over here is a function. Okay. The first functions that you studied in Algebra 1, in fact, were linear functions. Linear functions are lines, basically, right? And you're probably most familiar with them in the y equals mx plus b form, where m, of course, is the slope, and that's defined as change in y over change in x, or y2 minus y1 over x2 minus x1. And these are all concepts that we're going to use, so you have to actually get very familiar with these. So y equals mx plus b, where m is the slope, and b, of course, is the y-intercept, or where the line, the linear function, crosses the y-axis. Okay, so y equals mx plus b is the slope-intercept form. So this is called the slope-intercept form. Okay. There were 2 other forms which are actually very, very useful, and you have to get to know them. In fact, the standard form is ax plus by equals c. Okay, now this is the standard form. The standard form of a linear function is ax plus by equals c, and you have to be able to recognize it. So if you're given something like 2x plus 3y equals, like 7, you have to recognize that that's actually is a linear function. That's a line. All right. So the way you graph this, if you recall, is you make a baby table, x and y, and then you get the 2 intercepts. You put 0 over here, 0 over here, and find the value of y, and here you find the value of x. So this gives you 2 points. You only need 2 points to graph a line. 2 points to determine a line. So once you get those 2 points, you substitute 0 for x, get y, and then the second time around you substitute a 0 for y and get x. So you got 2 points over here, and then you plot them all over here, and then you can draw the line. Okay. Now, these 2 points, in fact, that you get by substituting x for the first time and substituting 0 for x the first time and substituting 0 for y the second time, okay, they give you the y-intercept and the x-intercept respectively. So the way you get x and y-intercept is by substituting 0 for one of the coordinates of the ordered pair. So the way you graph a line in the standard form is by getting 2 points. And the easiest point to get are the x and y intercepts. One will have x as the ordered pair. Let me make sure you understand that. See, every y-intercept of every line that exists, if it has a y-intercept, if every y-intercept will have x to be is 0, and y value will be some line on the y-axis, and every x-intercept for every line, if it has an x-intercept, because it doesn't have to, it could be like a horizontal line like this, every x-intercept will have some x value over here. We'll have some x value over here, and the y value would be 0 like this. That's for every x-intercept for every line. So the easiest way to draw a line that's given to you in the standard form is to find this x and y intercepts. Right? First time you can substitute 0 for x. If you substitute 0 for x, you'll get the y-intercept. And then if you substitute 0 for the y, you can get the x-intercept. So when you're given a line in the standard form, right, the way you graph that is by getting the x and y-intercept. I'm making a baby table like this, and then graphing the line in that manner. And the third way of writing a line is the point and shoot form, if you recall. Okay, that's y minus the y1 is equal to slope times x minus the x1. This is a very, very useful form, and we're going to need these. For example, the reason I'm placing such emphasis here is because we're going to need all this knowledge for this chapter. For example, to draw hyperbolas, you're going to have to find the equations of the lines, the asymptotes for the hyperbola. So we really need to kind of master this for this chapter. So this is the slope. This is the point slope form, or point shoot form, as I like to say. This is the point slope. That's the technical name. I affectionately I'll call it point shoot form because you can remember it that way. That is, in this case, we are given a point that's on the line. See, x1 and y1, they represent a particular point that's on the line. It could be this point, it could be this point, it could be this point, but this point is on the line. Okay, and this of course is the slope. So we're given 2 pieces of information in this form. So here is an example of a line that's given to us in the point slope form, and you have to recognize that this is a point slope form of a linear function. In this case, the point that we're given is -2 and 3 minus. Remember, there's a minus sign over here. -2 and 3, and the slope over here is 1/2. Right? So you have to recognize all of these forms, and you have to know them inside and out. Alright, so these are linear functions. There are 3 ways of writing linear functions. The standard way over here, and this is of course the slope-intercept form, and this is the point-slope form. And these are all linear functions. So here's, just for the sake of argument here, here's a line. Okay, that would be the y-intercept, right? And the slope would be change in y and change in x, like this. Okay, so that's a review of linear functions. Okay, next up are the quadratic functions. So I'm going to write this: quadratic functions. Now these are parabolas. Okay, and I'm reasonably confident actually that you know this. What, for example, now I'm confident that, inshallah, that you know these, the quadratic functions. The specific definition that we had for quadratic functions is that they are second degree polynomial functions. So if you have ax squared plus bx plus c. So quadratic functions, if you remember, these are second degree polynomial functions. Okay, see that these are second degree polynomial functions. Now, if you remember, the degree is the highest exponent that's in the rule. So if this is x squared, so that's the degree. Linear functions, in fact, first degree polynomial equations. Okay, so quadratic functions, the more precise definition for them is that they are second degree polynomial functions, right? And if you remember some of the terms, this is called the leading coefficient, and the c over here, that's called the constant term, and b here is just the coefficient of the second term that's given here. So that's the leading term with the leading coefficient, which is going to be very important to us in this particular chapter. So that's the leading term with the leading coefficient, and c is the constant term. This is the standard form of a quadratic function. And the way you graph that is, first, if you remember, as one of my favorite students of all time said, you have to first find the vertex. So the Vx is opposite of b over 2a. Okay, so opposite of b over 2a will give you the x coordinate of the vertex. And once you have this, you place that in the function. You replace that in the function to find the y coordinate. So you use this to find the Vy. Okay, the vertex, if you remember, the vertex is like this. Let me just draw over here like this, the vertex over here, and the vertex has two components: the x coordinate of the vertex and the y coordinate of the vertex. So the ordered pair of the vertex, the Vx and the Vy. That's the ordered pair. And the way you find the Vx is by this rule that we know in the standard form. Okay, so this is the standard form of the quadratic function. Right, now the very useful form is this one that you also know: f of x equals a times the quantity x minus Vx squared plus Vy. Now this is the vertex form. So the vertex form is very useful because it kind of gives you the vertex as a gift. And here's the x coordinate of the vertex, here's the y coordinate of the vertex. So the vertex form gives us the vertex, right? And that's very useful. And the third form is the x-intercept form: a times x minus s1 times the quantity x minus s2. Okay? So this one gives you the two x-intercepts. So here's a parabola, and those are the two x-intercepts. If it has x-intercepts, so here's a parabola that has no x-intercepts, right? So if it has x-intercepts, it will give you these two x-intercepts, those the x-coordinate of those ordered pairs. Okay, the y-coordinate of the x-intercepts will be 0, of course. So this is the x-intercept form, okay, of the parabola, of the second degree polynomial function. So these are quadratic functions, all right, and these are very important. That's the standard form, and that's the vertex form, and this is the x-intercept form. Okay, so in drawing a parabola, if you can, the first thing to do is find the vertex and plot it. And then the second most important thing, once you have the vertex, is to draw the axis of symmetry, like I'm doing here. Once you've drawn the axis of symmetry, then you know half the graph will be on either side of the parabola, and then it's going to be symmetrical. And so once you get one side, you can just reflect it on the other side like this, right? So as soon as you have the vertex, you draw the vertex, and the second thing you do is you draw the axis of symmetry, like here. Okay, once you have drawn the axis of symmetry, it becomes so much easier to draw the graph. Okay, so this is a review of some of the basic functions. And inshallah, when we have an opportunity, we'll try to review the remainder of the functions, but this much knowledge we really need to proceed with chapter 8. Until then, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.